All right, it's Friday. Who's happy that it's Friday? Who's sad that it's Friday? Who's excited about the exam that follows this class? What's it in?
Chemical engineering, transport phenomena.
Transport phenomena. That sounds fun. Because it's been a long week, it feels like the longest week of the year to me. I'm giving treats to all. I've been a little bit cheap about this, so we're starting in the back. There you go. Okay, the other thing I'm going to do is, while I'm talking, I'm going to have Brian, it has been a long week, pass out the other gift of the day, which will be a quiz that we're working. So you can do it in groups. I'm going to do it towards the end. I can't guarantee that we're going to have enough time to finish it, so that's why I'm putting it out there. The other thing is that I have a doctor's appointment at 2:15, so I have to run out the door and then race down to the other side of Ames. Okay, so please make sure that your group puts all their names on this half sheet, and then when we get to it, we'll get to it. So some things coming up.
Does everyone get one, or is it?
It's groups. So groups of 4.
Okay.
And if you want to squeeze 5 in there, that's fine. And if you're an isolationist, a group of 1 is fine. You know, whatever works. Okay? You can do that. You're probably going to have to move closer together, but there's time because we haven't started that part of it, right? Okay, so at any rate, exam 3 is just around the corner. 1 week from today, Brian will be presiding over the first of the review sessions. The study materials are posted, and I've warned everybody before, this particular exam has usually a lower average than the others. All right, so please buck that trend. You have done so on previous exams, so keep that up. All right, what we've talked about previously, we've looked at reversible isothermal expansion and compression of a gas, and we found that delta S is nR ln V2 over V1. That's the entropy change for the system, right? We looked at the bigger picture for that, and we saw that as long as the process is done reversibly, delta S of the surroundings is the same magnitude as delta S of the system, but with the opposite sign. So they sum to 0. And what we can conclude from that is a reversible process, which is by definition at equilibrium every step of the way, has a delta S equal to 0. So that's going to come up again. All right. We also looked at a variety of paths that ultimately are isothermal expansion and compression, and we showed that delta S is the same no matter how we go from the initial point to the final point. And so we've basically reiterated that entropy is a state function. We also looked at the definition of ds, the definition of entropy, and we saw that if we add heat to the system, dq is positive. If we take heat out of the system, dq is negative, and that reflects the change in the entropy. So if I have 2 objects, one at 1,000 K, one at 10 K, and there's the same material, same size, the entropy of the high temperature object will be greater than that of the low temperature object. All right. The other thing that we looked at was the addition of heat to 2 systems, and we looked at this generically, and then we did a calculation where we actually calculated delta S, looking at the same substance, heat transferring from one to the other. And what we saw for this was that delta S was a positive value. That meant the entropy of the system went up as a result of the spontaneous process, right? And because it was an isolated system, delta U was equal to 0. So this tells us that if we have isolated systems and there's a spontaneous process that occurs in there, the entropy is going to go up. Okay? All right, some other things I wanted to talk about before we get into things. We've previously shown that NKB is the same as NR. We're going to use that identity today. The other thing I wanted to do is just take a moment to look at our definition of ds. I can rearrange that definition and say dq reversible is the same as TdS. All right? Make sense? All right, we're going to see this show up in future chapters as well as in the upcoming chapter. So if I have the reversible heat transfer, dq, infinitesimal, that's the same as TdS. Okay? All right, so some questions that we're going to answer today. We're going to look again at heat transfer between two systems at different temperatures and talk about delta S. It's a little bit less concrete, more abstract than the example that we calculated last time. Then we'll do a global summary of the first and second laws of thermo, thinking about it from the universal perspective. And then from there, we're going to go into talking about statistical thermodynamics. So we're going to introduce S equals KB ln W and use it in a variety of ways. All right. The other thing that I just wanted to mention is up to this point, we've been confining our discussion to irreversible process or to reversible processes. We know that in the real world, most processes are irreversible, so we need to talk about delta S with that in mind. Right? All right, so what we're going to start with in section 6.4, this is a discussion of the second law of thermo. And basically what we're going to see, and we've alluded to this already, is that entropy increases for an isolated system as the result of a spontaneous process. My spelling is not going well today. All right, and the other thing I'm going to say at the outset is we know that if we have an isolated system, that necessarily delta U of that system has to be equal to 0. Okay? All right, what we're going to do is a thought experiment that parallels the calculation that we did last time. So we're going to talk about having two different systems. We're isolating them from the surroundings. So this represents, a really thick styrofoam box. I'm going to separate it into two parts. So I have a rigid wall. And we have one side that has a volume associated with it. It has a temperature associated with it. And then I have another side that's got a volume associated with it and a temperature associated with it. Okay? And the fact that, and I've got gases in here. Okay? All right, so the other thing that we recognize is I've introduced this rigid wall. We're going to allow heat to transfer. Right? So we'll just say heat can transfer. So if we think about the two modes of transferring energy, heats one, works the other. What does this rigid wall prevent? It prevents a volume change. So we're limiting ourselves to heat transfer, no work. Okay? All right, so what we know, because it's insulated from the surroundings, is that the total energy of the system will be given by the energy for side A plus the energy for side B, right? And because we're completely isolated, we know that the change in the energy of the system overall will be equal to 0. Okay? All right, so let's talk a little bit qualitatively before we start looking at some equations. So let's say TA is higher than TB, right? Do you expect something to occur? Yes. What do you expect to have happen? You're going to approach equilibrium, and how do you do that? What's going to be transferred? Heat energy, right? And it's going to flow from side A to side B. So Q from A's perspective will be positive or negative. Anybody? It's going to be negative. And Q from B's perspective will be positive, and they'll be the same magnitude. Right? We agree with that? Okay? All right, so the other thing that we can say at this point is that the entropy of our system will be given by the entropy for side A plus the entropy for side B. All right? And what we're interested in doing is taking this and determining what the change in entropy is due to the spontaneous process that we expect to occur. All right? So let's start. We know that dUA is equal to dQ reversible plus dW reversible. And we know because we've forced the situation to have no change in volume that this is equal to 0. Okay? Does that make sense? All right. The other thing that we know is that dQ reversible is related to the entropy through the definition of entropy, right? So we can say that dQ reversible is the temperature times the change in entropy for that side. All right, so that will be TA dSA. Does that make sense? All right, to save time, we know that side B is going to be the same, but now we're just talking about the reversible heat transfer with respect to side B. So that means that's going to be equal to TB dSB. Make sense? Okay, because these are equal to du, then what I can do is I can rearrange these for dSA. So I can say dSA is equal to du for side A divided by the temperature of side A. All right? So I've taken this, divided both sides by temperature. All right? I do the same thing for side B. So ds side B is going to be equal to du side B over TB. Okay? All right. And then from there, we can say, well, ds is going to be equal to the summation of ds for side A. Right? So the overall change in the entropy of our system is going to be due to the change in entropy for side A plus the change in entropy for side B. That in turn is dUA over TA plus dUB over TB. Okay? We want to simplify this a little bit. What's the relationship between the change in the energy of side A versus the change in energy for side B? Equal but opposite sign. All right? And so what I can do then is I can take minus dUB and substitute that for the change in the energy for side A. All right? So I'm going to scroll down to this. So we're going to pull dUB out. All right? I got this weird page break that showed up in my thing. So at any rate, I'm substituting minus dUB here. I can pull out dUB. That's going to put a negative 1 over T, positive 1 over TB. So it becomes ds equal to du for side B over 1 over TB minus 1 over TA. Okay? So we've derived an expression that tells us ds in terms of the two temperatures and the energy flow into or out of side B. All right? Let's look at some examples. The first case is if TA and TB are equal to each other, what's ds equal to? It's going to be equal to 0, right? Because 1 over TB, 1 over TA are the same. They annihilate, right? So I end up with 0, right? And if you think about it, if my two sides are at the same temperature, do you expect any future change to the system? No, that means we're at equilibrium. All right, so we've demonstrated that for our system, if the change in entropy is 0, that means we're at equilibrium. Or if we know we're at equilibrium, nothing's going on, that means that ds is equal to 0. Okay, so next up, let's look at the two other possibilities. One is that side B is hotter than side A. Right? So if side B is higher temperature than side A, heat will flow into A from B. And that means dUB will be greater or less than 0. Less than 0. All right? So applying that to my equation, that says this term is negative. All right? Was there a question? All right. Okay, so next up we need to determine what the sign is of this. So I'm going to take 1 over TB, compare it with 1 over TA. All right? So if TB is greater than TA, what's the relationship between the reciprocals? 1 over TB will be less than 1 over TA. Everybody get that? All right. So when I come over here, this is saying that this term is larger than this term. That means it dominates, and this is going to be overall positive or negative. It's going to be positive. All right? So we've established, or not positive. Wait, hang on a second. Whoa, whoa. This dominates. That's a negative. So it's going to be a negative term. Right? So we've established that for this case, ds is greater than 0. Okay? So the spontaneous process that occurs accompanied by an increase in the entropy. All right, look at the opposite case. So now I've got side A is a higher temperature, side B is a lower temperature. That means we expect heat to flow from side A. Therefore, it's flowing into B. dUB is going to be greater than 0. Right? That makes this term positive. Right? And then whenever I look at the reciprocals, now because the larger temperature is TA, that means this is smaller than this is. This term dominates, and this is overall positive. Okay? And a positive times a positive gives us a positive. All right? All right, so basically what this has shown us is that if I have an isolated system and I have a process that occurs on its own, it's going to be accompanied by an increase in entropy. Let's say that you do a calculation and you find that ds is negative for an isolated system. What does that tell you? It's not going to be spontaneous. It's not going to occur. Okay? Does that make sense? All right. So if I have a spontaneous process, ds is greater than 0. All right? All right, so again, just to compare things with the first law, if I have an isolated system, we know that there's no change in the energy of that system. However, if a spontaneous process occurs, entropy increases. All right, and because of the way this works, right, the system's isolated. That means that this entropy change is directly a result of the fact that we had a change occur, right? So the entropy is produced by the process. We indicate that with DSPROD. We're going to use that in a little bit. So this just means the change in the entropy of the system is due to a spontaneous process. Okay? All right, and then the other thing that we can do is think about this a little bit more globally. So as a function of time, if I have an isolated system, and I'm plotting entropy as a function of that, let's ask this question. Let's say that I'm starting, my system is at that point in entropy. If it's at equilibrium, whenever I come to a later time, where is it? It's the same. We have a horizontal line, right? If I'm not at equilibrium, then we expect the entropy to start out at whatever point we're at, and with time, it's going to go up, and as it approaches equilibrium, it's going to level off, right? ds equals 0 is where equilibrium has been attained, right? And for a given system, that will represent the maximum entropy that that system can have. Okay? All right. This is a little bit of review of some things that we've said previously. But because the concepts can be a little confusing, I tend to reiterate things that are at least things that I think are important. So we've said that a reversible process is at equilibrium every step of the way. And so as long as I have a reversible process that's in an isolated system, that means that ds will be equal to 0, or delta S will be equal to 0, right? We didn't mention this whenever we talked about the reversible adiabatic expansion. But if you think about the reversible adiabatic expansion, we didn't let any heat come into the system, right? We didn't let any heat transfer out. And what we saw was delta S for that process was equal to 0, okay? And that's because we did it reversibly. All right, so next up what we want to talk about is if I have a system that's not isolated. That means it can interact with the surroundings. And we ask the question, what makes up that change in entropy? Well, part of it will be ds produced, right? That will be due to the process itself. Right? The other input is we know that once it's not isolated, we can have it interact with the surroundings. And if we think about the definition of entropy, ds is dq over t. So it's the heat transfer that becomes important, right? So the second input is heat transfer with surroundings. And we're going to symbolize that with ds exchange, EXCH, right? Just to be consistent with the textbook, right? And so globally for this system, we can say that ds is given by ds produced by the process plus ds due to heat transfer with the surroundings, okay? All right. And if I isolate the system, that makes this go to 0, okay? All right, so if we think about a reversible process, what we've just stated is that we expect that the change in the entropy is going to be at 0 because it's at equilibrium all the time, right? And under that situation, ds exchange will be dq reversible over t. And putting these together, as long as I'm talking about a reversible process, ds will be given by dq reversible over t, right? Right? There's really nothing new there, right? That's our definition of entropy. Then if we talk about an irreversible process, one that we're more likely to observe in the real world, what we know is that ds of that process has to be positive, right? So it's going to be greater than 0, right? And then ds exchange, well, that's going to be dq irreversible over t, right? Because we're not performing this reversibly. So this is the heat transfer for an irreversible process. And then putting these two together says that I don't have an equality anymore. What I can say is that the change in the entropy for this open system is going to be greater than dq irreversible over t. Okay? All right, we're going to be using this expression in a little bit. Okay. And then rather than having to think about whether it's reversible or irreversible, we can combine these into one equation. And that basically is stated as ds greater than or equal to dq. And this could be reversible or irreversible, so it's just generally dq over t. Okay? All right, and so basically if we step back, this is basically saying our entropy change for our process is either going to be equal to dq over t, that means it's a reversible process, or it's going to be greater than. Okay? This is called the inequality of Clausius. I always feel like when I say that, there should be like a fanfare, you know? Wouldn't you like your legacy to be inequality of, Joe or Adrian? Yeah? No? Okay. Well, whatever. Okay. Although Clausius carries more clout than Joe. All right. So next up, what we want to do is we want to talk about the entropy change that's associated with an irreversible spontaneous process. Okay? All right. What we're going to do is construct a cycle. We're starting at step 1, or state 1, ending up at state 2. I'm going to travel from 1 to 2 by an irreversible process. But we're also going to choose it to be isolated. Okay? And basically what we want to do is show that entropy increases if I have an irreversible process, right? We've talked about what happens for a reversible process. Now we're talking about irreversible, right? So I really want to know what delta S is for this, and that will be given by S at state 2 minus S of state 1, right? So that's our goal is to get this, okay? All right, and then what I'm going to do is complete the cycle and say once I'm at state 2, I'm going to come back to my initial state, and I'm going to choose that path to be reversible. And we're going to allow heat exchange. So heat exchange with surroundings permitted. Okay? All right, so for delta S of the cycle, if I asked you, what's the entropy change for me going from here to here and back, what's it got to be? It's got to be equal to 0, because entropy is a state function, right? So it doesn't matter where I go. If I say, wait, end up at the same point, it's going to be equal to 0, right? And that's going to be equal to delta S for the irreversible process. That's the upper trace, right? Let me add IRR under that. Plus delta S for the reversible process, which corresponds to the return. Okay? All right, so what we're going to do is a series of substitutions. So delta S for the all right, I want to make sure I don't muck it up here. All right. So what we know is that delta S for an irreversible process is going to be greater than dq irreversible over t integrated, right? And we're going from state 1 to state 2, so it's going to be the integral from 1 to 2. Okay? All right. And then for the reversible process, we know that's an equality, and that will be equal to the integral from state 2 to state 1 dq reversible over t. Okay? All right. So we come down here, and this is delta S for our cycle, right? We know that's equal to 0. And now I need to include delta S for the irreversible and delta S for the reversible, and I don't have an equality anymore. Yeah?
Why do you have an equality instead of equals for the delta S irreversible?
Where is the equality?
Or equal is greater than.
Okay, because that's what we've shown in this previous slide. All right? Because if I have an irreversible process, we only know that the process, the spontaneous process itself, has a greater than 0 change in entropy. And then by irreversible, the exchange with the surroundings, dq over t, putting those two together, this has to be greater than dq over t. All right? So it comes back to this. Okay? This isn't easy. I mean, conceptually, this is hard to wrap your head around. So I'm trying to make it clear, but go back and look at it so that it makes sense to you. Okay? All right, so at this point, I can say that delta S for my cycle is this, and now I want to include these two terms, and putting those together, what I can definitely say is that 0 is greater than the sum of delta S, irreversible and reversible. So that'll be 1 to 2 dq irreversible over t plus 2 to 1 dq reversible over t. Okay? All right, the other thing that we can do is we can do a little bit of simplification here. When we chose to come along this irreversible path, we said that this is isolated. That tells us that the heat transfer is 0, right? So we can say that dq irreversible over t from 1 to 2 is equal to 0 because dq irreversible is 0 according to the way that we've designed the thought experiment. Okay? All right, and then we look at this second one, right? And we see, all right, this is the definition of ds. And the integral of ds is delta s. And in this case, that's going to come out to be s1 minus s2 because we're talking about the return path. That makes sense? That means that the only thing on this side is s1 minus s2. So at this point, we can say 0 is greater than s1 minus s2. Okay? All right, now keep in mind that what we're looking for is delta S of the irreversible path, which is S2 minus S1. So we're close. What do I need to do to get this to S2 minus S1? I need to flip it. And how do I do it? I multiply it by -1, right? So when I multiply it by -1, that becomes 0, S2 minus S1. What happens to my greater than sign? It flips, and it becomes less than. All right? And what we can conclude then is that delta S for an irreversible process is greater than 0. Okay? All right. Summary, entropy increases if my system's isolated, even by an irreversible process. So we've talked about reversible, irreversible, isolated systems, and then the impact of having interactions with the surroundings. Okay? All right, now we want to think about things a little bit more globally. So the universe is an isolated system as far as we know, all right? And so what we can say from the point of view of the universe is that for the first law, energy U is it changing? What's the first law of thermo? It's an isolated system, right? So nothing's coming in, nothing's coming out as far as energy goes. That means it has to be equal to 0, and the energy of the universe is constant. All right? If we turn our attention to the second law, we're talking about entropy. All right? And what we've established is that if we have an isolated system that's not at equilibrium, that means if something's happening in your system without outside intervention, the entropy has to be going up, right? And you guys are not stagnant, right? You're getting older, I'm getting older, right? Things are changing, right? The universe is getting bigger, right? So entropy is increasing overall. Okay? All right, so next up, we want to shift gears a little bit, and we want to talk about the thermodynamics side of entropy. So we're going to start by talking about entropy of an ensemble, which we've previously said is given by KB ln W. All right? So this is where what we introduced in the math chapter is going to be applied. Right? So previously, we've shown that the ways of arranging objects into groups is given by taking the number of objects, factorial, over the number of members of one group, another group, and factorial for all of them. All right? Now, we're not so interested in objects. What we're interested in are systems in our ensemble. So if we go back to our concept, we have this huge ensemble of systems. They all have the same temperature, they all have the same volume, they all have the same number of moles of particles, right? So we can say that the number of ways of arranging those systems in the ensemble into various groups is going to be given by big A, where that's the number of systems in our ensemble, right? And the groups that we're thinking about are the different quantum states that we can possibly have for these different systems, right? So this is where it might be helpful to think about a dice or think about a penny, right? So if I have a dice, a single die, I've got 6 quantum states available to it, right? Okay? So one group would be when it's 1, one when it's 2, etc. Right? So in the denominator, I can say A1, that's the number of members of a given quantum state. And then I have the other quantum states, A2, all the way up to A omega, right? And omega is the number of degenerate states, okay? So for the case of a dice, a single die, I have 6 equivalent states. So that means omega would be equal to 6, right? Now, if you think about it, if you took a die and you rolled it 10 million times, well, actually, for ease, let's say you rolled it for 6 million times. How many times do you think you'd see 1? More than one. But you'd tend, if you roll it that many times, you'd expect to see 1 million, 1 come up 1 million times, and 2 come up 1 million times, right? Okay? And so if we have a situation where we have the same number of systems in all of the quantum states, then this denominator becomes something a little simpler. So if A1 equals A2 equals all the way up to A omega, then what we can say is that this denominator becomes A factorial raised to the omega power, right? Because every one of these is the same, and I've got omega terms. Make sense? Okay? All right, so the other thing that we need to keep in mind is the sum of the number of members of each of the groups. So the number of systems in this quantum state, number of systems in this, I sum over all of them. That has to be the total number of systems in my ensemble. Okay? All right, so what we're going to do is we're going to talk a little bit about what this means for a couple different situations. All right, so if I have everybody in the same state, so let's say that I happen to have 10 million die, or 6 million, well, it doesn't matter, 10 million die, and every one of them had 1 on it. That means they're all in the same quantum state, right? So in that situation, the total number of systems will be equal to the number of members of one of the groups, all right? And that means that the number of all the other groups is going to be equal to, help me out, it's going to be equal to 0, okay? All right, so plugging that in, we can say that S equals KB ln A factorial over A factorial, and then I put in for my other groups 0 factorial, 0 factorial, 0 factorial. And what's 0 factorial equal to? It's equal to 1, right? So this becomes the natural log of 1, all right? And what's the natural log of 1? It's equal to 0, okay? All right, so this tells us is if we have a perfectly ordered system, the entropy is equal to 0, all right? Little foreshadowing. This is different than when we talk about energy, right? We've talked about U, the energy of the system. And one of the things that we know is that energy of the system is going to be the kinetic energy. That, we talked about translational, vibrational, and everything. But we didn't talk about the things that we can't access easily, the potential energies, right? And if you think about when we calculated energy levels, we always had to choose an arbitrary 0 point, right? It wasn't a real 0 point. It was arbitrarily set. In this case, we have an absolute 0 point. And that means that we can talk about absolute values of entropy. All right, so the other thing, and we've alluded to this before, if I'm talking about maximum disorder, the maximum value of W, in order to get there, what I'm going to have is an equal distribution of my systems into all the quantum states. Right? So at that limit, A1 equals A2 equals A3 all the way out. And that gives us our maximum entropy. Right? And we're going to be using that concept in a little bit. Okay? All right. So the other thing that we want to talk a little bit about is, does this definition work the way that we expect it to work? So the thing that we've seen earlier today is that we had a side A with an entropy and a side B with an entropy. And we said that the total entropy of the system is given by the entropy of side A plus side B, right? So we want to make sure that this function SKB or KBLNW gets us there, all right? So if I have two sides or two systems together, one A, one B, if this is the number of ways of arranging A and this is the number of ways of arranging B, the number of ways of arranging everything is given by, and we'll talk about that in a minute. Let's say we're talking about pennies, right? If I have a penny, it can be heads or tails. So what's the number of ways of arranging one penny? 2, all right? And if my other system consists of one penny, it's going to be 2. And if I have 2 pennies together, how many ways are there to arrange it? Head, 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 tail, tail, head, tail, tail, head, right? It's the product of the two. Does that make sense? Right? So we can say that W is given by the product of WA times WB. Right? If this doesn't make sense to you, also think about a dice. Right? Same concept. All right, so that means that I can say that the entropy of our ensemble is given by KB ln WA times WB. All right? So I've got the natural log of a product, which we know can be separated into a sum of the natural log of each of the components of the product. So that's equal to KB ln WA plus KB ln WB. Right? And this is going to correspond to the entropy of A. Right? That's the definition. That'll be the entropy for system B. Okay? All right, so now we're going to talk about things that are a little bit more practical. And this is where we're going to see a convergence between the classical starting point and the statistical thermodynamic starting point. All right, so entropy, we will see, we're going to derive this, is that for a single system in our ensemble, an average system, is given by KB ln omega, where omega is the degeneracy of the quantum states. Okay? All right, so we know that we have big A number of systems. Right? The other thing is that we're talking about at equilibrium. So at equilibrium, we expect the system's entropy to be at its maximum. That occurs when we have equal distribution of systems in our ensemble into the different degenerate quantum states. All right. And that means that A1 will equal A2 equals A3. All right? Okay, so just to make this a little bit less abstract, if I choose an ensemble that has 100 systems and my degeneracy is 5, we're basically saying we're going to have 20 systems in each of those degenerate states, and A1 equals A2 equals A3, and that equals 20. All right? So one of the things that we can see at this point is that the number of members of one of the groups, number of systems in an ensemble, times the degeneracy, that's going to get us the total number of systems. So we can say that A is equal to n times omega, where n is the same as the number of members of a given quantum state. Right? On this derivation, I want to apologize for something, but I need to be consistent with the textbook. I think they've added in some variables that aren't necessary for a clean derivation. I don't think we needed to add the n in, right? But I want to be consistent with the text. So just keep in mind, n omega gets us the total number of systems, and then n is just the number of members of one of our groups or quantum states. Okay? All right, so given that, we start with our definition of entropy. S of our ensemble is Kb ln W. What I can do now is I can say at equilibrium, this is going to be Kb ln A factorial, where that's the number of systems in the ensemble, divided by, because we're at equilibrium, in the denominator we've got A, little a. Good luck. Make sure you put your name down on the quiz. Yep. All right. Little a factorial omega. All right. So we've already talked about that. Okay, so at this point, I've got the natural log of a fraction, so I can separate that to the natural log of the numerator, natural log of the denominator. This is a factorial raised to the omega power. I can pull omega out front. Now what we're going to do is we're going to introduce the Stirling approximation. We're going to say we have lots of systems in our ensemble, so A is very large. So that allows me to say natural log of a factorial is a ln a minus a. Similarly, for the natural log of little a, that becomes little a natural log a minus a. All right? Okay, so all I've done here is rewrite the Stirling approximation for the number of systems in the ensemble and the number of systems in a quantum state. Okay? All right, so then I have to plug that back in. We know that A is equal to n times W, or n times omega, and A is equal to n. So that first one can become n omega, because that's the same as big A, natural log of n omega minus n omega. All right? And then doing the substitution for this second equation gets us n ln n minus n. All right? So now I'm going to take this, plug that back in here. So that means I need to multiply it through by omega, right? And then this one, I just need to multiply both of them by kb. So this is kb. Here's the natural log of large A factorial. And then this is n ln n minus n times omega, all right? And I'm subtracting the two as we expect to do. We see we're going to cancel n omega. We also see in front of the natural log, we've got n omega, so I can pull that in front. So I now have n omega kb ln, right? Now if I pull those out in front, then I've got the summation of, or natural log of n omega minus the natural log of n. That can be combined into a single fraction. All right, and then that single fraction, that will become n omega in the numerator and n in the denominator. N's cancel, and I'm left with this equation. All right? So this is the entropy of our ensemble. All right? And if we think about it, our ensemble has got n omega as the number of systems, right? That's A. So if I divide this by n omega, that's going to be the entropy for one system. And what we've shown is that the entropy of a single system is given by kb ln omega. Okay? All right, so then the next thing that we need to do is say, well, how do we get at omega? How do we get at the degeneracy? And the derivation we don't have time for in this class. I really feel sort of guilty about that, but it is what it is. All right, so that degeneracy is going to be given by a constant that depends on the number of particles. It's also going to be given by that times a function. And that function depends only on the energy of the gas. Right? And if we're talking about an ideal gas, what does the energy depend upon? It depends on temperature, right? And then the last term in there is the volume raised to the number of particles. Okay? All right, so this is the quiz part. We'll just work it through on here because it's here, rather than having you guys work it on there. Just make sure your names are on there. And we're not going to do that till Monday anyways. That's a clean place for us to stop. I'm 2 minutes behind where I was this morning.